Welcome to this tutorial on developing models with C++ in SystemVue. You may have an algorithm implemented in C++ or C and now want to bring it into SystemVue to test its performance with realistic channel models or circuits such as a power amplifier. We will start with an overview of the software development environment and how it ties in with SystemVue. We will then create different models in this tutorial to highlight the important features. So let's start with an overview. This SystemVue schematic contains a C++ model and a measurement setup, the same as what you would use in a lab on a scope. This other screen shows a software development environment based on Visual Studio C++. Here you can manage the build process with CMake. You can edit your code. You can compile your code. And once the build is complete, you can run it in SystemVue and measure its performance. So you have an integrated development environment with Visual Studio and SystemVue. As of the creation of this video, which is based on the 2022 version of SystemVue, you need to install Visual Studio version 2019 along with the C++ compiler. Now let's get started with creating our first model, and for this we will start with a new blank project in SystemVue. You can read the documentation about C++ models, which is accessible from the Help menu. The introduction shows the different steps involved. There are three major steps. In the first, we use the GUI in SystemVue to create a Visual Studio project. It will create a directory structure and populate them with some basic files. We next edit the CMake files and add C++ code and compile. Finally, we bring the model back into SystemVue and simulate. To start, select Action, Create Model Builder Project, give your project a name, select where you want to save this project. Since we want to use the final model back in SystemVue, we must specify the name of the library in SystemVue where the model will appear. Now select the Create button and SystemVue will create the project directories and launch Visual Studio. Now let's examine the directory structure of the project just created. There are two subdirectories, a build and a source directory, and a batch file. Here are the contents of the batch file. It includes the path to the CMake executable, which is shipped with SystemVue. It creates a build directory and runs CMake from this location. The output goes to this output-vs29 directory, and the input to CMake is from the source directory one level up, and we will examine its contents next. The source directory contains another CMake file. In turn, it includes a CMake file from the SystemVue installation directory, the details of which are not necessary now. It then adds a SystemVue subdirectory. This SystemVue subdirectory is where your C code will reside. And here you will edit the CMake lists.txt file and add your files into the build process. The build directory contains the Visual Studio project with extension .sln. You can restart Visual Studio with this .sln file to restore the project. There are 4 solutions shown here in the Solution Explorer window in Visual Studio, and the source files are under SystemVue Test1. Instead of starting from scratch, you can generate a template header and C++ file for your model as follows. Edit the cmakeLists.txt file and uncomment and edit the following lines. The argument to the macro SVU create model is the name of your model, and we will call it M1. Next, scroll down and uncomment and edit the following two lines. By selecting the installed solution with the right mouse button and select Rebuild. After this step, .h and .cpp files for the model M1 are generated. The header must include the model builder.h header file. The model C++ class must be derived from SystemVue model builder df model. The macro declare model interface with the model name as argument M1 must be called in the public area, and it declares an interface between the model and the simulator. By default, a constructor, a virtual method called run, an input port, an output port, and a parameter called gain are declared. The run method is where the computation gets done, and it is called by the simulator. There are other virtual methods which will be called by the simulator, and they are defined here. The methods are setup, initialize, run, and finalize. This simple model does not need them all, but we will see some of them when we create a more complicated model. The input and output buffers are managed by the simulator, so you, the user, must not allocate or destroy the memory for these buffers. The semantics of data flow guarantees that the input buffers will have valid data each time the model's run method is invoked. The type of circular buffer defined here is of type double. There are other types of circular buffers, and they correspond to the different signal types in SystemVue. We now look at the C++ file of the model. The macro define model interface specifies the interface between the simulator and model. The same inputs, outputs, and parameters from the header file need to be added here. The gain parameter can be initialized to any value in the constructor. The run method does the calculation and sets output equals gain times input. The model produces one output for each input sample, and hence the input and output buffers are of size 1 and accessed by the index 0. We can now compile the model. To import the model back into SystemVue, go to the SystemVue window and select Tools, Library Manager from the menu on top. Select the Add from File button in the Library Manager window and navigate to the Output VS 2019 directory of the project. Select the debug build directory and the test1.dll file. Click the Open button. Scroll in the Library Manager till you see the project name. Select it by checking the box to its left. Next, go to the Paths Selector window, and the project just created should show up in the Current Library drop-down menu. The part just created should be listed below. We next show how to add other types of models. To add the models, start with the cmakeLists.txt file in the source directory and add a SVU create model macro for each element. Also, add lines for the corresponding C++ and header files. Create the template for these files by selecting Install Build from the Solutions window as before. The files are now created. Model M2 is an example of a model with multiple input and output ports. The header file, m2.h, is as shown for multiple input and output ports. This is the syntax in m2.cpp to register the model with all its pins, parameters, with the simulator using the define model interface macro. Finally, the computations are done in the run method. Model M3 is an example of a multiple rate element. There is now an additional method called setup where the rate of each pin is specified. The default value is 1. The user can specify the rate with a parameter, and it is set before the simulation starts. The rate of the input pins is set to the parameter rate in the setup method. Note that the rate of an input pin is the number of samples available at that pin when the run method is called, and the rate of the output pin is the number of samples that must be placed in it by the run method. Since the input buffer is of size rate, these values are accessed as input 0, input 1, up to input rate minus 1. In this case, the output rate is 1 and the single output sample is set equal to the average of the input samples. Finally, compile the code as before. If we now look in SystemVue in the part selector window, the new elements will appear with the right number of pins and parameters. In this tutorial, we have shown how you can add your own C++ code as a model into SystemVue. We have shown some of the important features for creating different kinds of models. More details are available in the documentation. Thank you for watching the tutorial.